Eurocircuits are a European manufacturer of standard technology printed circuit boards, or PCBs. We specialise in providing prototype and small batch PCBs for designers, product development departments, niche market electronics companies, universities and research establishments. We've made this film to help electronics engineering students understand how a PCB is made. In this film, we will show the manufacture of a 4-layer multi-layer. This covers all the different processes used in PCB production. Front-end tool data preparation. The board designer has prepared his layout on a computer-aided design or CAD system. Each CAD system uses its own internal data format, so the PCB industry has developed a standard output format to transfer the layout data to the manufacturer. This is extended Gerber or RS-274X. The Gerber files define the copper tracking layers, 4 in the job we are following, as well as the solder masks and component notations. First we check that data meets our manufacturing requirements. These checks are mostly done automatically. We check the track widths, the space between the tracks, the pads around the holes, the smallest hole size, etc. Once the data is verified as good, he will output all the tool files needed to drive the machines that will make and test the PCB. Preparing the photo tools. We use laser photo plotters in a temperature and humidity controlled darkroom to make the films we will use later to image the PCBs. The photo plotter takes the board data and converts it into a pixel image. We've generated one film or photo tool per PCB layer. Now the films are registered with each other so that the different layers of the PCB will be perfectly aligned. We do this by punching precise registration holes in each sheet of film. The operator puts the film on the table of the punch and then micro-adjusts the table until the targets on the film are exactly lined up with the targets on the film punch. She then punches each sheet of film with the registration holes which will fit into the registration pins in our imaging equipment. Print inner layers. To produce the inner layers of our multi-layer PCB, we start with a panel of laminates. Laminate is an epoxy resin and glass fibre core with copper foil pre-bonded onto each side. The first step is to clean the copper. The clean panel is coated with a layer of photosensitive film, the photoresist. The bed of the printer has registration pins matching the holes on the photo tools. The operator loads the first film onto the pins, then the coated panel, then the second film. The pins ensure that the top and bottom layers are precisely aligned. The printer uses powerful UV lamps which harden the photoresist through the clear film to define the copper pattern. Under the black areas, the resist remains unhardened. Outside the yellow room, the panel is sprayed with a powerful alkali solution which removes the unhardened resist. The copper pattern we want is now covered by the hardened resist. You can now see in the blue resist what will be the copper on our inner layer panel. Etch inner layers. We remove the unwanted copper using a powerful alkaline solution to dissolve or etch away the exposed copper. The process is carefully controlled to ensure that the finished conductor widths are exactly as designed. Next, we strip off the blue photoresist which protected the copper image, so now we have the exact pattern required. Register punch and automatic optical inspection. The inner core of our multi-layer is now complete. Next, we punch the registration holes we will use to align the inner layers to the outer layers. We won't be able to correct any mistakes on the inner layers once we've assembled the multi-layer, so we now give the panel a complete machine inspection. The automatic optical inspection system scans the board in broad strips and compares it with the digital image generated from the original design data. Layup and bond. The outer layers of our multi-layer consist of sheets of glass cloth pre-impregnated with uncured epoxy resin, or pre-peg, and a thin copper foil. The layup operator has already placed a copper foil and 2 sheets of pre-peg on the heavy steel base plate. Now he places the pre-treated core carefully over the alignment pins. Then he adds 2 more sheets of pre-preg, another copper foil and an aluminium press plate. He then rolls the heavy stack under a press which lowers down the steel top plate. The press operator collects 3 stacks on a loader and loads them into the bonding press. This press uses heated press plates and pressure to bond the layers of the PCB together. The heat melts and cures the epoxy resin in the pre-preg, while the pressure bonds the PCB together. The process is computer controlled to build up the heat and the pressure correctly, hold it, and then to cool the press down. In this way, we ensure a permanent bond that will last the lifetime of the PCB. Once the cycle is completed, the press operator unloads the press and carefully rolls the heavy stacks into the clean room. Here, the layup operator depins the stack and removes the top plate. The copper foil is now bonded in place to form the outer layers of the PCB. Drilling the PCB. Now we drill the holes for leaded components and the via holes that link the copper layers together. The operator first puts a panel of exit material on the drill bed. Then he loads 1 or more PCB panels and a sheet of aluminium entry foil. The drilling machine is computer controlled. The operator selects the right drill program. This tells the machine which drill to use and the XY coordinates of the holes. Our drills use air-driven spindles which can rotate up to 150,000 revolutions per minute. High-speed drilling ensures clean hole walls to provide a secure base for good plating on the hole walls. Drilling is a slow process as each hole must be drilled individually. So depending on the drill size, we drill a stack of 1 to 3 PCB panels together. We can drill holes down to 100 microns in diameter. During bonding, excess resin from the pre-preg is squeezed to the edge of the panel outside the image area. This excess is now cut off on a computer-controlled profiling machine. Electroless copper deposition. The first step in the plating process is the chemical deposition of a very thin layer of copper on the hole walls. Almost all PCBs with 2 or more copper layers use plated through holes to connect the conductors between the layers. A good connection needs about 25 microns of copper on the walls of the holes. This thickness must be electroplated, but the walls of the holes are non-conductive glass cloth and resin. So the first step is to deposit a conductive layer over the hole walls. We use Electroless copper. That is, we deposit chemically a layer of copper about 1 micron thick over the walls of the hole, and incidentally across the whole panel. We pre-treat the panel, then we seed the whole wall with microparticles of palladium, and finally deposit the copper. Image the outer layers. We image the outer layers in a clean room to make sure that no dust gets onto the panel surface where it could cause a short or open circuit on the finished PCB. The panel is first coated with a layer of photosensitive film, which is hot rolled onto the copper using a cut sheet laminator. For inner layers, the copper pattern we want was covered by the resist. For outer layers, it is exposed, ready to be plated. The imaged panel is conveyed out of the clean room and through a developer which removes the unhardened resist. Plating. Next, we electroplate the boards with copper. The panels themselves act as cathodes, and we can plate the whole walls thanks to the conductive carbon layer already deposited there. The copper surface of the panels is cleaned and activated in a number of baths and then electroplated. To ensure good conductivity through the holes, we need to plate on average of 25 microns of copper on the whole walls. This means that we also plate 25 to 30 microns on the surface tracks. Once we have plated the copper onto the board, we then plate a thin layer of tin. This we will use in the next step of the process, when we etch off the unwanted copper foil. Etch outer layers. The copper is covered with a thin layer of tin as an etch resist. Now we will remove the unwanted copper foil from the surface. We do this on a single continuous process line. The first step is to dissolve and wash off the resist which covers the unwanted copper. Then we remove the unwanted copper using a powerful alkaline solution to etch away the exposed copper. The process is carefully controlled to ensure that as we etch down, we don't etch sideways as well. This means that the finished conductor widths are exactly as designed. Finally, we strip off the thin tin coating which protected the copper image, so now you can see that only designed copper pattern remains. Apply solder mask. Most boards have an epoxy ink solder mask printed onto each side to protect the copper surface and prevent solder shorting between components during assembly. Each panel is given a final clean to remove any dust from the surface and loaded into the vertical coater. The coating machine simultaneously covers both sides of the panel with the epoxy solder mask ink. The panels are now racked and put through a conveyorized dryer which hardens the resist just enough to allow it to be printed, or tack dried. Next, the coated panels are imaged. As with the etch and the plating resists used earlier in the process, the UV lamps in the machine harden the ink where the film is clear. That is where we need solder mask on the finished board. The imaged panels are put on a conveyor out of the clean room and into the developer, which strips off the unhardened and unwanted resist. Later, the required resist will be further hardened or cured to provide a robust and permanent coat. But first, the operator checks the alignment of the solder mask on the panel and makes sure that there are no traces of ink on the pads or through the holes. Even slight traces will compromise the solderability of the finished PCB. RoHS-compliant surface finishes. Electroless gold over nickel. The copper component pads and holes have been left clear of solder mask. Now we apply a solderable surface finish to protect the copper until the components are soldered onto the board. On this line we chemically deposit first nickel onto the copper and then a thin coating of gold over the nickel. This is a chemical process needing no electrical connections. The line is fully automated, moving the panels through a series of tanks which clean and sensitize the copper surface and then deposit about 5 microns of nickel and 1/10 of a micron of gold. Silkscreen and cure. Most PCBs have a component legend to show which component goes where. Today we use inkjet projectors to image the legends direct from the board digital data. Like a conventional paper printer, the inkjet printer sprays minute droplets of ink onto the panel to generate the image. If a legend is needed on the second side, the ink is tack dried on a conveyorized heater and the printing process is repeated. Now we finally cure both the epoxy ink solder mask and the legend. Electrical test. Using a flyer probe tester, we check each net to ensure that it is complete, no open circuits, and does not short to any other net. A faster test method is the Acceler 8. This uses 4,000 tiny probes like a brush. It builds an electronic map of the PCB from a preheated good board. Then it compares each board to be tested with its map. This cuts test times by 90%. Profiling. The final manufacturing stage is to profile the PCBs and cut them out of the production panel. For this we use computer-controlled milling machine, or a router. First the machine mills out any small slots or internal cutouts. Next the milling head automatically picks up a 2mm cutter, checks the diameter and mills around each PCB. The circuits are held in place by small bridges of material. We will drill through these and then remove each separate PCB from the production panel.